Welcome back to topic 47 for Algebra 2, Inverse Functions and Relations. In part 2, we're going to see if we can identify a function and its inverse by a graph, as well as find an equation of an inverse function and then graph it. So how can we identify a function and its inverse by the graph? First, we're going to represent the inverse relation algebraically. So in this example here, we have f of x equals x squared. Now, I'm first going to rewrite this as y equals x squared. We know that f of x and y are interchangeable. Now, as we learned in part 1, we're going to switch x and y. So this will give us x equals y squared. Now we're going to solve for y. In doing this, we're going to take the square root of both sides and we'll get plus or minus the square root of x equals y. Or if we want to rewrite it, y equals plus or minus the square root of x. There we go. Now in part B, we're going to look how are these graphs actually related. So I'm going to graph the first function in green here. So y equals x squared. Now this is the parent function of the quadratic function. So we're just going to graph that here. Now if we wanted to graph our inverse function, which I will do in blue right here, I'm going to graph that on the same graph to see how the two graphs are related. You can also do this by using a table of values and plugging in numbers for x and getting your output y. Now, what do we notice about these two graphs? Well, for our first parent function, the y equals x squared, our green graph, it looks like that graph was rotated 90 degrees. In actuality, this is called it's reflected. It's reflected across the line y equals x. So, in other words, the inverse of f, our original function, is the reflection of the graph y equals x squared across the line y equals x. So this is where we have a y-intercept of 0 and a slope of 1. Moving on to part C though, I want to consider my function f of x equals x squared. Now we had our inverse function that we had in blue here. But specifically, under what domain will the inverse relation be a function? Because it's not guaranteed that the inverse is a function. So if we look at our first graph for y equals x squared, or f of x equals x squared, we have this parent function here. If we look at the domain and range of this parent function, what do we get? So we have f of x equals x squared for the domain. The domain is all of your x values. So if we were to zoom out on this graph, we were to go from negative infinity to positive infinity. Those are all the possible values of x. The range is all of my y values, and notice how the range, there's nothing below that x-axis, so the smallest possible y value that we could have is 0. And since there's a fixed point there, that's why we're going to use a bracket. Whereas infinity is indefinite, so that's why we're going to use a parentheses. Now, as we learned in part 1, for an inverse relation, the domain and the range of a relation switches. So if I want to write the inverse of this, I would get f inverse of x. Now we just identified on the previous slide, once we calculated this algebraically, we get plus or minus the square root of x after swapping x and y and solving for y. Now since we know that the domain and range swap, for our inverse relation here, our domain would be 0 to positive infinity, because the range becomes the new domain. And then our new range would be our old domain, which would be negative infinity to positive infinity. However, if we were to graph that, we would get this blue graph right here. But what do we notice about this original blue graph? Well, if we were to draw a vertical line through it, we would notice that it would hit our graph more than once. So it would fail the vertical line test. Hence, this inverse relation would not be a function. Now, instead of taking the time to first graph our function and then identify what the inverse relation would be and then graph that inverse relation to see that, we kind of have a trick that we can use here. Notice how in our original function we have f of x equals x squared. If we look at this graph, we notice that there are two values here. Two different x values that have the same y value. We have 2, 4 and negative 2, 4. So in order for our inverse to be a function, we need to note that all of these duplicate y values, because we have a 4 here and a 4 here, need to be eliminated. In other words, we need to restrict our domain. So it's this part right here that is preventing this relation for being a function. it's this part right here for this example. The graph shows that it fails the vertical line test. Oops. So in other words, what we do need to do is we need to restrict the domain so this doesn't happen. Because remember, the original domain becomes the new range when we're dealing with inverse relations. So the domain is where we need to put our focus. So with our new function, we have f of x equals x squared. What can we do to the domain so that when we translate it and identify our inverse, that inverse is a function and not just a relation? Well, if we look back at our graph right here, it's this line that was kind of causing the problem. So I'm going to put it in dash so we still see it, but this is the part that we want to kind of adjust, I should say. So we only want what's to the right of the origin right here. In other words, our domain is going to be from 0 to positive infinity instead of from negative infinity to positive infinity. And we can look on our graph right here. If we see that it's reflected across the line y equals x, it's this part right here that would be reflected down here. And it's this bottom half right here that is causing the issue. So as a result, we need to fix that left side of the original graph, the part where our domain is anywhere less than 0. Now, the range is still going to stay the same. It's just anywhere that's 0 and up. So when we adjust our new inverse, instead of f inverse of x is going to be plus or minus the square root of x, we're just going to focus on the positive square root of x. So it's just positive right now. Actually, let me do blue. So it's all color coordinated. So we're still going to do the same thing where our domain and our range swap. So our domain is going to be the previous range, which is going to be from 0 to positive infinity. And then the range is going to be the previous domain, which is also going to be, in this case, 0 to positive infinity. So if we were to graph this now, this is what our graph will look like. It will only be the top half of this. And this graph passes the vertical line test. So in other words, we needed to restrict the domain of our original function, so of f of x, to be x is only greater than or equal to 0. Remember, it's greater than or equal to, so that's why we have a closed bracket. Instead, I should say, so it changes from 0 to infinity instead. So our inverse function right now is just f inverse of x is positive so the plus side of the square root of x, so just the positives. And that is now a function. I know this slide is a little jam-packed. So let's see if we can summarize this. So if we notice from our first function, we had these 2 points, -2, 4, and 2, 4. So if a function has 2 or more, I should say, x values for the same y value, so we had that 4 repeating, and we can draw a horizontal line through it where it touches more than once, its inverse will not be a function because it will fail the vertical line test. So we can kind of think of that like horizontal and vertical are inverses, and we're dealing with inverse functions here. So if it fails this horizontal line test, such that the horizontal line hits more than one point on our graph, then it will also fail the vertical line test. The inverse, I should say, will fail the vertical line test. But there's a way to change this. So we can restrict the original domain in many different ways to create a function that will have the inverse, so that we will have an inverse that is a function. So if we want to summarize this, if a function passes the horizontal line test, sometimes it's often referred to as is 1-to-1. So in other words, it will only touch this horizontal line once. The graph will only touch this horizontal line once. Or it is 1-to-1. Then the inverse is a function because it will pass the vertical line test. Okay, so let's find an equation of an inverse function. Here we have an equation of the inverse function or we're asked to find an equation of the inverse function f of x equals the square root of x minus 2, and then asked to graph it. So here our parent function is a square root of x function, which we know is the same thing here. We're going to take that parent function, but because we have this x minus 2 in our radicand, what we're going to do is with that parent function, we're going to shift it to the right 2 units. Remember, if it's inside the radical, or in the radicand, then that relates to a horizontal or vertical shift. And since it's minus, we're going to shift to the right. It's kind of the opposite of what we think. So let's take this original function. I'll do it in green just like we had before. And we can also create a table of values to do this. I'm just going to graph it since it's that original parent function, but just shifted over 2. And there's my function. Now we know again we have this we have this line of y equals x, not a vertical line. And the inverse will be reflected across that. So if we look at the original domain and range of our first function, we know that for all of our x values, it starts at 2 and goes off to positive infinity. The range, nothing is below the x-axis, so our smallest possible value is 0, and it goes to positive infinity. If we want to write this in, since this is interval notation, if we want to write it in inequality notation, this basically is just saying that our x values could be 2 or greater, and our y values could be 0 or greater. Now for our inverse function, remember our domain and range is going to switch, and then we're going to see if this actually is a function or if it's just going to be a relation. So we're going to swap these. And remember, when we swap, our variables are also going to swap. So domain always deals with our x variables, range always deals with our y variables. So for the inverse for the domain, it's going to be from 0 to positive infinity. In other words, x is going to be greater than or equal to 0. And for our range, it's going to be from 2 to positive infinity. In other words, y is going to be greater than or equal to 2. So since we have our original function as y equals the square root of x minus 2, remember, if we want to find the inverse, we're going to swap x and y and then solve for y. So this is going to change to x equals the square root of y minus 2. Now we're going to solve for y. So we can square both sides, and we will get x squared equals, oops, forgot to square the right side, equals y minus 2. Remember, we have the square root and it's raised to the second power. Those undo each other, so we're just going to be left with the radicand. So x squared equals y minus 2. We can add 2 to both sides. Oops. And get x squared plus 2 equals y. So in other words, our inverse is going to be f inverse of x is the same thing as x squared plus 2. So this is our parent function, our parent quadratic function of x squared, but because we have this plus 2, this is like our plus k, we have a vertical translation up 2 units. So now I'm going to graph that. And we can see our original function of f of x equals the square root of x minus 2. It's reflected across this line of y equals x. And now we can kind of double check and make sure our domain and range are match this. So for our x values, we start at 0 and go off to positive infinity. X is greater than or equal to 0, that's correct. And then for our range, we have nothing below this point. Our y value here of 2, and it goes up to positive infinity. So that is also correct. So we found our inverse, we graphed it, and also confirmed our domain and range. That was part 2 of topic 47 for inverse functions and relations for Algebra 2. Thank you for watching.